Hello and welcome to another WJEC A level physics question. This is question 2 from May 2014 Unit 1, and it's a question about a spring that's obeying Hooke's law. So what we've got to start with is a graph showing the applied force against the length, and the first thing we're asked to do is state Hooke's law. Now there's not a lot of room here, so we can actually just, especially because it's 1 mark, just get away with a simple statement that the force or the load is directly proportional to the extension. Ideally, we'd also want to add into that, provided that we haven't exceeded the limit of proportionality, but there's not really enough room for that. Next, we're going to determine the spring's unstretched length. So if the spring isn't stretched, there's no force acting on it, and when there's zero force acting on the spring, we can see from the graph that its unstretched length will be 4.0 centimeters. Next, the spring is used as a simple accelerometer, a device for measuring acceleration. The spring is attached to a 0.4 kilogram mass, which is placed on a friction-free surface as shown, and the device is installed in a car. The car accelerates uniformly from rest, and we've got to calculate the acceleration when the spring is extended by 12 centimeters. And we're going to use this information and the graph to calculate the car's acceleration. Well, if the spring is extended by 12 centimeters and its original length was 4 centimeters, that means its new length will be 16 centimeters. And if we read 16 centimeters off the graph, just being a little bit careful with the scales, you will see basically that the force is 0.6 newtons. So if the resultant force is 0.6 newtons, then we can apply sigma f equals ma, or a equals sigma f over m, to find the acceleration. So sigma f was 0.6 newtons, the mass was 0.4 kilograms, and that's going to give us 1.5 meters per second squared. And this question was actually a unit mark question, so you'd have dropped the mark if you'd forgotten meters per second squared. We've got to calculate the elastic potential energy in the next part of the question, stored in the spring when the car's acceleration is the same as it was in B. So we've got an extension of 12 centimeters. We can use, for example, the formula that the elastic potential energy is half Fx. So it's a half times the force, which we read off the graph, 0.6 newtons, times that extension of 12 centimeters. So we've got to remember that's 12 times 10 to the minus 2. So I'll just put those into the calculator, and we end up with 0.036 joules. For part 2, we've got to calculate the the elastic potential energy stored in the spring when the car's travelling at constant velocity. Well, here the resultant force would be 0, so there would be no extension. And if there's no extension, there's no elastic potential energy stored. So our answer here is simply 0. For the last part of the question, the accelerometer is modified by attaching a second identical spring to the mass, as in the diagram. And we've got to explain the effect that adding a second spring has on the extension and the total elastic potential energy when the car's acceleration is the same as it is in B. Well, for the extension, just consider the fact that that force is being split equally between the two identical springs. So each spring experiences half the force compared to B, and therefore half the extension. So let's write down something along the lines of force is shared between the springs. The force in each halves. And going back to Hooke's law, force proportional to extension, therefore the extension halves. Next, to consider the elastic potential energy. Well, let's go back to that formula that elastic potential energy is a half Fx, and consider each spring. Each spring has half the force in it and half the extension. Now a half times a half is a quarter. So let's put that down. So each spring stores a quarter of the previous energy, or the energy in B. There's 2 springs, so the total energy stored is a half of B. Thank you very much for listening. Please remember to like and subscribe, and feel free to add any comments below. Goodbye now.